Speaker Yihui. Yeah, okay. The last announcement. Professor Ma will deliver a talk on ICANX in November. Yeah, it already confirmed. Yeah, so we're looking forward to have your talk here. Yeah, today is like a rehearse. Yeah. Okay. Yeah. Thank you.
Thanks for
Yeah.
having me here. Thank you. Thank you.
Okay. Now we move to the second speaker, Yihui Zhang. Yeah. Professor Zhang Qing, please, is your job now. Yeah. Go ahead. Okay, Tim, please turn on your microphone. You're mute.
Okay, thank you, Alice. And it's my honor to host Yihui's talk at ICANX. I give a short introduction of the Professor Yihui Zhang. He's an outstanding professor, young and outstanding professor. And he's a professor of the engineering and mechanics at the Tsinghua University. And he's received several honors and the awards. I just list a few, including the MIT Technology Reviews, 35 Innovators Under 35, and the ASME Thomas J.R. Hughes Young Investor Award, and also NSFC Excellence Youth Fundings, etc. He's also the associate editor of the Mechanics of Materials Research and the ASME Journal of the Applied Mechanics. And he and his group, a major focus of his research is the study of the flexible mesostructure technologies, and it's also the topic of his talk today. So Yihui, please start your talk. We are looking forward to it, please.
Okay, thank you, Tim, for the nice introduction. So can you hear me? Can you see my screen?
Yes, we can hear you. Yeah.
Wonderful. Hello, every online audience. Firstly, I would like to take this chance to thank Alice for the kind invitation. The ICANX Talks is a very magic platform, and with honor, I really appreciate this opportunity to introduce the research of my group. So today I'm going to talk about the recent progress of my group in flexible mesostructure technologies, with a focus on the design, fabrication, and yield properties and device applications enabled by these technologies. We all know that most biological systems and human organs have complex while delicate 3D construction at the micro and nanoscale, such as the DNA structure, the mitochondrion, blood cells, pulmonary alveolus, and the vasculature of heart, as well as the bone structure of human. Such complex 3D nano, micro, and mesostructures not only form naturally in biology, but also provide the most essential functions. Therefore, if we can develop design and manufacture approaches to achieve analogous artificial 3D architectures, with similar geometries, physical properties, and functionalities of biological systems, it will undoubtedly have important implications in many, many areas. Actually, the research over the last decade has already yielded substantial advancements in the field of material science that draws inspiration from the nature. This has already become an important approach to the design and synthesis of new materials and interfaces. So as you can see from this slide, the bio-inspired materials and structures have found applications in a broad range of areas, from our daily life to sports and military technologies. We know that the existing studies in this area focus more on reproducing the microstructure geometries and physical properties as compared to reproducing their functionalities. Meanwhile, the bio-inspired the soft biological tissues and organs have received less attention as compared to the hard biological materials. On the other hand, the non-infectious chronic diseases have been the leading cause of deaths globally for many years. In 2012, these diseases caused 68% of all deaths, according to the report of World Health Organization. In this regard, the long-term real-time monitoring of physiological signals is very crucial because they can provide quantitative feedbacks for the early stage prevention of these diseases. And for this purpose, the functional devices are usually required to be conformably integrated with human organs. And therefore, the 3D functional microstructures with similar shapes and mechanical properties to those of biological systems can provide an important platform to interface and merge biology with physical components. One of the technological challenges we face is in the development of soft architected materials with customized mechanical properties. In particular, how can we develop rational material designs that can utilize microarchitectures in traditional materials so as to achieve mechanical properties that mimic or exceed those of soft biological tissues? It's noteworthy that by using conventional engineering materials, the fabrication is highly simplified and more straightforward. But the difficulties here include how to reproduce accurately the complex and even irregular microstructures of soft tissues, as well as how to understand the structure-property relationship. If you want to further add some functions to those 3D an urgent need is to develop 3D microelectronics with desired 3D geometries. As you can see in this slide, because the microelectronic technologies have already approached their physical limits, we can see an evident lag between the prediction of Moore's law and the development of integrated electronics. So there is a clear gap here. Since the third dimension can provide brand new opportunities, the 3D micro and nano electronic devices has already become an important research direction in the era of post-Moore's law. Here, a grand challenge is in the development of manufacture approaches that can enable the formation of complex flexible 3D mesostructures in inorganic semiconductors and other high-performance materials. So the single crystal silicon is a good example, which represents the hard material of the current information industries. To address these challenges, my group has been engaged in the development of flexible mesostructure technologies through the use of mechanics principles and highly interdisciplinary studies. According to these technologies, we have developed unusual soft architectural materials that can reproduce and even exceed the mechanical properties of soft biological tissues. We have also developed a mechanics-guided assembly approach that can enable the construction of 3D flexible electronics with brand new functions. Here I will start with the introduction to the soft architectural materials with customized mechanical properties. In particular, we have developed a class of soft network designs and manufacture approaches. The key idea is to incorporate strategically designed filamentary microstructures into the lattice network and to utilize the composition design and geometrical optimization to tune the effective mechanical properties of the soft network. On one hand, we have developed design strategies to achieve biomimetic properties as well as unusual properties that do not exist in natural materials. The examples of these properties include, for example, the biomimetic J-shaped stress strain curves, the imperfection-sensitive behavior, as well as unusual responses of swelling, thermal expansion, and Poisson's ratio. On the other hand, it is crucial to develop quantitative mechanics models that can serve as the design basis and to dictate the structure-property relationship. Additionally, we are also interested in exploring some unique applications enabled by these soft network materials. Great. So let me first show you the bio-inspired network designs. As you can see from the left two images and the right top image, the collagen fiber is usually composed of irregularly distributed helical structures that are connected at certain joints. So you can see clear helical structures here. And under uniaxial stretching, this helical-shaped collagen fiber unfurl, straighten, and stretch in a manner that gives a low modulus as a small strains, but with a sharp transition into the high modulus regime at large strains. So the result is a J-shaped stress strain curve, as you can see here. The bio-inspired deterministic design we propose is shown in this slide. So here, the key idea is to develop an engineered artificial polymer in which the helical microstructures inspired by the collagen fiber serve as building block structures, and the lattice pattern form a regularized network. Actually, different lattice topologies can be exploited, and here are 3 examples, including the cubic network, octahedral network, and the octet network. So here, the images on the top show the cartoons of our design, including the lattice pattern, the helical microstructures, and the unit-cell structures. And on the bottom shows the optical images of our 3D printed samples. So here, with the use of the commercial PolyJet 3D printer, we can achieve a robust production of the soft network materials with a fiber diameter down to around 200 microns. The video here illustrates that the fabricated soft network material can undergo large levels of stretching, compression, bending, and twisting. And during this loading and unloading process, the microstructure deformations are basically elastic and reversible, according to our mechanics modeling. Actually, this kind of soft network design can provide access to a broad range of J-shaped stress strain curves, and our mechanics modeling allows us a clear understanding of the structure property relationship. And with this, we can perform inverse design of the soft network material to reproduce accurately the stress strain curves of biological tissues. So here are 2 examples. On the top, if you look at the black curve here, this corresponds to the stress strain curve of a real heart muscle. The blue dots here represents the results of artificial tissues based on our network design. So you can see good agreements between our artificial tissues and the real heart muscle. And on the bottom shows another example for the right ventricular myocardium of an adult rat. And here, the mechanical responses are very different between the circumferential and the longitudinal directions. And even for such anisotropic nonlinear stress strain curves, the artificial tissues based on our network design can still reproduce accurately the stress strain curves along both directions. If we degenerate the 3D helical structures into 2D, we are able to create a class of 2-dimensional network materials. And this kind of 2D network material can be tailored to reproduce the stress strain curves of film-like tissues, like animal skin. And this kind of 2D network material can be fabricated much more easily than the 3D networks. So excluding the 3D printing, the photolithography and the laser cutting technologies can be also used, and either the polymers or the metals can be exploited as a solid material. So here is an example of the fabricated network wrapped onto the tip of the thumb. Actually, human skins show different mechanical properties for skins at different locations or people with different ages. For example, if you compare your skin at the abdominal region between your skin at your back, you will see that the skin at your abdominal region is much softer, and you need to apply a very large strain before it reaches its hardening region. Instead, if you stretch your skin at your back, you just need to stretch it very slightly, and then you will step into the hardening region. So it's a very big difference. So here, this kind of mechanical response has been tested for real skins at different locations, as you can see on the right. So here, the back 1 and back 2 represent 2 different locations on the back. And based on the mechanics models we published in JMPS and JM in 2016, we are able to achieve artificial skins that can reproduce accurately the stress strain curves of human skins at different locations. So you can see good agreements between our artificial skins and real skins. Okay. So this kind of soft network materials can be used in a skin-like ECG sensor to provide a good platform for the stretchable biomedical devices. And by doing so, we can not only achieve a conformal contact with the skin, but also the biomimetic properties. And another device demonstration is shown on the bottom. So here we can use the antenna to wirelessly control the release of responsive hydrogel into the surrounding tissues, into the surrounding environment. And here the mechanism is the electromagnetic coupling. Actually, this kind of soft network material also show biomimetic imperfection in sensitive behavior. We all know that with a brittle solid material, there will be a strong stress concentration around the hole. And this will result in a very big reduction in the strength, typically around 60% of the original strength for ideally brittle materials. And the stretchability is also reduced significantly. And here we show that even when we use the macroscopic brittle material to construct this soft network material, both the strength and the stretchability are quite imperfection insensitive. So we have studied a range of different circular holes with different sizes and different positions, and here is a representative result. As you can see here, the blue color denotes the stress strain curves of a perfect network material, and the red color denotes the stress strain curves for an imperfect network with 6 missing microstructures in the center. And in this condition, the strength is only reduced by around 20%, and the stretchability is reduced only by 10%. So in practical applications related to stretchable electronics, we usually want to utilize some holes in the network to accommodate some functional chips or some other electronic components. So here is the demonstration of a stretchable LED device based on the soft conducting network. And this device can offer a stretchability of around 14.2%. And this value is very close to the value 15% of the perfect network. And this device also offers a very stable mechanical and electrical properties. Excluding the biomimetic properties, we also want to achieve some unusual properties that do not exist in natural materials. So one of the properties we studied is the unusual response of swelling, such as a large lactive swelling. So this requires the material to shrink largely during water absorption. And here the key idea is to incorporate heterogeneously integrated microstructure into the lattice network. And this video shows the construction of this composite network. And in short, we want to devise a kind of filamentary microstructure that shrinks largely during water absorption. And this drives us to look into this kind of sandwich design with a passive layer to serve as a support and a thin encapsulation layer to ensure a good interface between the hydrogel and the polymer support. And such a sandwich design can easily transform the swirling deformations of the hydrogel into a large bending deformations, and therefore this can achieve a large reduction in the end-to-end distance. And this kind of composite network can be fabricated using the multi-material 3D printer. So you can use a commercial 3D printer to achieve this production. And on this slide, it shows the simulated deformation process during the water absorption and dehydration. And you can see the predicted deformed configurations agree very well with the optical images in experiments. And if you calculate the value of linear swirling ratio, you will see that this fabricated network can offer a very large elective swirling ratio of around 50%. And this corresponds to around 70% reduction in the area. And this is unachievable previously. And when you do dehydration, this kind of structure can recover almost fully to the initial state. This indicates a good reversibility. Good. And based on this kind of soft network design, we are also able to achieve anisotropic swirling behavior by using heterogeneous microstructures in the network. So here is an example. If you put hydrogels only along the diagonal directions, you can achieve a kind of unidirectional shrinkage along the x direction and no shrinkage or expansion along the y direction. If you describe this kind of swirling path in the space of string components, epsilon x and epsilon y, we can do a comparison between the current metamaterial design with the traditional engineering materials as well as previous metamaterial design. So actually, the traditional engineering materials only offer a very small magnitude of swirling ratios, typically within this region. The well-synthesized hydrogels can offer very large swirling ratio. It can go beyond 150%, but typically in an isotropic manner. So it is in this path. Professor Katia Botoni's group at Harvard proposed a metamaterial design that can achieve an isotropic elective swirling ratio of around 20%. Therefore, there are many blank areas in this strain space, and the soft network designs we propose can well fill almost all of those blank areas. So this indicates the capability of our soft composite network design. The above design concept of heterogeneously integrated soft microstructures can be also extended to achieve unusual modes of thermal expansion. Here you need to introduce two materials with a relatively large difference in the coefficient of thermal expansion. And we choose Pi and PMMA as the two constituent materials. And in terms of the fabrication, it could be a challenge, especially when you want to achieve a very small feature size of around several tens of microns. But due to the time limit, I will skip the details of the fabrication and just show you some results. So on the right, you can see this kind of metamaterial that can achieve a unidirectional thermal expansion. So there is low shrinkage or expansion along the horizontal direction. By introducing some non-uniform arrangement of the microstructures, we can also achieve this kind of thermally induced pure shearing, rotation plus shearing, as well as thermally induced bending. And most of these behaviors does not exist in natural materials as well. Excluding the unusual responses of swirling and thermal expansion, we have also explored the unusual responses of Poisson's ratio. So for traditional cellular materials, they either offer isotropic Poisson's ratio at small strains or anisotropic Poisson's ratio at large strains. And it's very difficult to combine the two features together in a tunable manner. So here we have proposed to incorporate arbitrarily shaped microstructures into the lattice network, which allows us to achieve tunable isotropic Poisson's ratios at large strains. And actually, we have developed a mechanics model that gives an analytical solution to the linear Poisson's ratio for this general network material. And according to this analytical solution of the Poisson's ratio, we found that this kind of engineered zigzag microstructure is able to offer a very broad range of tunable Poisson's ratio from -1 to 1 in an isotropic manner. And this is also unachievable previously. Let me show you a video about what we can achieve. And here are 3 representative designs we studied both experimentally and theoretically. So by tuning the microstructure geometries, we can achieve a large negative Poisson's ratio of -0.5, 0 Poisson's ratio, as well as a positive Poisson's ratio about 0.5. And with this network design, we are also able to achieve a kind of artificial cat skin. So here we find that the cat skin at a certain location also show a kind of negative Poisson's ratio, as you can see here. And by using our soft network design, we can reproduce not only the nonlinear transverse strain, but also the J-shaped stress strain curve of real cat skin. And this slide shows the use of this soft network material to create an unusual cylindrical tube. So for this kind of cylindrical tube, when you stretch it, the left segment expands in the cross-section, the middle part keeps the cross-sectional area almost unchanged, and the right part shrinks along the circumference. If you further introduce the shape memory effect, the deformed configurations can be memorized in the freestanding state. And this feature can be utilized in the thermally-induced, thermally-triggered medical stents. Okay, I will give a short summary to the first part of the lecture. So in conclusion, we have incorporated the strategically designed microstructures into the lattice network with proper geometries and heterogeneous integration. And the result is a class of soft network material designs that can achieve both biomimetic properties and unusual properties of swelling, thermal expansion, and Poisson's ratio. We believe that there are many application opportunities in biomedical devices and tissue engineering. Then it comes to the second part of the lecture. And here, an important mission is to address the challenge in the fabrication and manufacture of flexible 3D microelectronics. To address this challenge, we started relevant studies from 2012, and now we have established an approach distinct from all of the previous ones. So the key idea is we did not abandon the well-established microelectronic technologies. Instead, we go one step further beyond the traditional 2D fabrication, and we exploit the compressive buckling to deform easily patterned 2D thin films into well-controlled 3D architectures. After devising this approach, an important aspect involves the exploration of the class of 3D geometries accessible to this mechanics-guided approach. Another fundamental question is, how can we develop quantitative models that can serve as the basis of inverse 3D design? In addition to developing the approach itself, we are also interested in exploring the unique applications enabled by this approach. So I will illustrate the process of this assembly on this slide. Firstly, we use a soft elastomer to serve as the platform, and we apply a biaxial pre-stretch to the substrate. And this platform will provide the forces required to induce the compressive buckling. Meanwhile, we can use the microelectronic technologies to create patterned 2D thin films in silicon and other high-performance materials, and then we integrate them together. And by using techniques of surface chemistry, we can create strong covalent bonding selectively only at the rest sites. The other places are simply weak interface and can pop up easily from the substrate surface if you release the pre-strain in the substrate. And then the 2D structure can be transformed into well-controlled 3D architectures. Since the microelectronic technologies can do mass production and thousands of components can be fabricated on the same batch, our 3D approach can also assemble thousands of 3D mesostructures at the same time. A powerful aspect of this approach is the broad range of applicable material types. In addition to the single crystal silicon, this approach also works well for metals, polymers, plastics, ceramics, piezoelectric materials, as well as flexible printed circuit boards. So if you do two-dimensional fabrication of the integrated circuits, the entire circuits can be transformed into 3D at the same time. Another powerful aspect of this approach is the broad range of applicable length scales. So unlike most of the other approaches, this mechanics-guided approach works perfectly well over a wide range of length scales, from submicron scale to metascale. In order to provide some intuitional impressions, we compare our assembled structures with some objects in real life. So here, the assembled structure at the submicron scale has a comparable dimension to blood cells. Adjacent to this microscale 3D structure sits a human hair. So you can see a human hair here. For millimeter and centimeter scale structures, we use a coin and a pen as a reference respectively. And the rightmost panel shows the largest structure we have achieved, which is comparable to a human body. So after my group and our collaborators published a few papers in this area, these works were quickly noticed by the editors of Nature Reviews Materials and Advanced Materials. And they invite us to write 2 review papers, and both were eventually published as cover articles. So if you look at this cover image, you can see that we actually use a kirigami design to achieve this tiger at the micro scale. You can imagine that this tiger is completely flat at the initial state, and we simply use the compressive button to trigger its pop-up into this tiger at the micro scale. In this direction, my group has the research of my group over the last few years has been focusing on 4 different aspects, including conceiving some new design concepts, developing robust design methods, inventing assembly instruments, as well as exploring new applications. In specific, the design concepts involve the designs of 2D precursors, the design of deformable substrate, and how you integrate them together. The development of design methods aims to answer the question of how to map the target 3D configuration onto the initial 2D patterns. The assembly instruments involve the loading and characterization of the soft-hard interface, the multi-field assembly, as well as nanoscale assembly. And in terms of the applications, we have explored the development of unusual electromagnetic devices, MEMS, and biomedical devices. So due to the time limit, I will show you some representative results in these different aspects. Okay, after we published the first paper of this area in Science in 2015, an intuitive idea is to introduce and extend this idea to the assembly of 3D membranes or 3D curvy surfaces. However, we noticed that a simple extension might cause some unexpected issues, as shown on the left of the slide. So if you put 4 bonding pads uniformly around the boundary of a circle or a square, you will observe evident localized deformations in the central area of the structures. This will result in strong strain concentration. And in this case, if single crystal silicon is used for the fabrication, then the structure will break because the peak value of the maximum principal strain is much higher than the fracture limit of silicon, which is around only 2%. So to address this issue, we introduced the design concepts of kirigami to change the load transfer path within the structure. So as you can see here, the localized deformations disappear and the strain concentration is relieved evidently. So here we introduce some pattern cuts. And you can see that the peak value of the strain is reduced from around 5% to only 1.3 and 1.5%. And in this condition, if single crystal silicon is used for the fabrication, the structure will survive eventually. Then I would like to show you an example that illustrates the assembly process for this 3D membrane structure. Here we actually use a set of fractal crosscut that divide this large square into 16 small squares, which are interconnected with each other. So here, this video shows the deformation process to result in this final 3D membrane structure. And this prediction agrees very well with our experimental results. So you can see here, this mesostructure has a literal dimension of only around 200 microns, and the thickness of the silicon is only around 300 nanometers. By introducing different types of kirigami designs, we are able to construct a diversity of 3D membrane structures. And here is the library of the 3D membrane structures we have constructed using this approach. And here, the first column of the table shows the 2D precursors. The second column corresponds to our simulation results. And the last column, and you can see good agreements between our prediction and the experimental results for all of those designs. Okay, you may notice that the 3D structures I just showed you are mainly in the ribbon shape or the membrane shape. And these structures are formed mainly by the bending deformations or twisting deformations. If you think about the origami techniques, an ancient art originated from China and Japan, you will see that many interesting 3D sculptures can be created using paper origami. The key to this technique is to form creases and folding deformations in a controlled manner. But at the micro scale, you cannot use your hand to fold those structures, right? So it literally brings us a question: can we generate similar folding deformations during the process of compressive buckling at the micro scale? And if so, how can we achieve it? Actually, we propose a very simple strategy by use of the non-uniform thickness distribution in the 2D film. In specific, we make the 2D film much thinner at the gray region so as to reduce the local stiffness. You can imagine that this gray region has a thickness of 1/10 of this blue region. Then during the compression, the bending deformations will be localized at the thin region so as to create this kind of folding deformations. So here we can do a comparison. If you use the uniform thickness design, then the deformations is rather smooth as shown here. But when you do this non-uniform thickness design, we can achieve this kind of folding deformations. And this video shows the use of this idea to create a 3D sockable structure. And the entire assembly process is completely reversible. And excluding this sockable structure, we can also achieve this car structure, windmill, pyramid, and many other origami structures. Great. In many of the previous studies, we always use the simultaneous release in the biaxial, in the substrate to form the 3D structure. The result is a deterministic 3D assembly, through the smooth, continuous changes of the 3D shapes. Here we show that for specially engineered 2D precursor designs, we can play with the release sequence to achieve multiple stable modes of the 3D structure. So this slide shows the key idea. And at the center shows a 2D precursor design attached to a biaxial pre-stretched elastomer. And here, the green color denotes the creases with reduced thickness, and the red color denotes the bonding paths. Okay, so when you release the biaxial pre-strain simultaneously, This structure will follow this deformation path, and finally you will get this shape 1 mode. But when you do sequential release with X first and Y second, then this X directional ribbon will deform into 2 waves first because of the constraint from the Y directional ribbon, which is completely flat. Then when you release the remnant Y directional pre-strain, then the entire structure will be trapped into this shape 2 mode. And finally, you will get this shape 2 structure, shape 2 mode. So this is a 2-wave mode. And actually, by stretching and releasing with different sequences, this shape 1 and shape 2 modes can be reshaped into each other reversibly. And actually, our microscopic experiment validates this idea, as evidenced by this good agreement between our experiments and our predictions of the 3D configurations. And then I would like to show you an interesting example of this 3D reconfiguration process. And this video shows the reconfiguration in a metal mesostructure with a millimeter scale copper as the material. So this panel shows the experiments, and this is the finite element results. And this panel shows the loading path. And when you do the simultaneous release of the pre-strain, you get an octopus structure. But when you do sequential release, you will get a spider structure. And actually, this octopus structure can be reshaped reversibly into this spider structure. And this kind of reconfiguration process is unachievable using the previous techniques. And such a reconfiguration process was luckily selected as a cover of Nature Materials in 2018. Good. So for the other structures without any symmetry, the sequential release along different directions may be induce different 3D configurations, okay? And here is an example. We can define the angle phi as the direction of the first step release of the biaxial pre-strain. So you can see that the sequential release with phi equal to 45 degree or 135 degree both give the same shape, mode 1. But the sequential release with the 90 degree direction give a completely different 3D shape, mode 2. And these 2 modes can be actually reshaped into each other reversibly, okay? To provide a design basis, we have used the finite element simulations to establish a phase diagram to show the buckling modes for sequential release along all possible loading directions, as shown here. So here, the green color corresponds to mode 2, and the yellow color corresponds to mode 1. So based on this phase diagram and a set of fundamental reconfigurable 3D structures, we can develop a bottom-up design strategy to form reconfigurable mesostructures with multiple stable modes. And this slide shows an example. By using 2 curvy ribbons as building blocks and collecting them together, we can create this kind of structure with 3 stable modes. So this is evidenced by this phase diagram. If you further mirror this pattern, we will get this kind of butterfly design with 4 stable modes. And this video shows the reconfiguration process for this multi-stable structure. And the 4 different stable modes are shown here. According to the above introduction, you can find that this kind of 3D assembly actually corresponds to a process of post-buckling deformations in thin film structures. To establish a theoretical basis of this 3D assembly, we need to first solve the forward problem, which is how to predict nonlinear post-buckling deformations for prescribed 2D precursors. And for this purpose, we have developed both energetic models and perturbation methods for the post-buckling analysis. In particular, for this double perturbation method, we introduce two perturbation parameters to linearize the nonlinear governing equations from which analytical solutions can be obtained for general ribbon shapes. And here, one of the perturbation parameter is related to the magnitude of deformation, which is widely used in the conventional perturbation method. And the additional perturbation parameter we introduced relates to the flexing level of the initial 2D ribbons. And as you can see here, the analytical predictions agree very well with our experimental results and simulation results. After solving the forward problem and gain some insights into the 2D, 3D relationship, we eventually want to establish robust inverse design methods. Specifically, how do we determine the initial 2D precursors, the bonding size and the pre-strain level for target 3D configuration? And this can be regarded as a type of optimization problem, and different algorithms can be exploited. So my group has proposed the use of adaptive genetic algorithm to solve the inverse design problem for the 3D ribbon structures. And based on a theoretical analysis for the geometrical relation between the deformed and the initial ribbon structures, we developed an optimization-based formulation of this inverse design problem. And the results on the middle and right shows an example of this curvy ribbon optimized from the target. And this slide provides some examples of inverse design through this optimization method. Here, the first column corresponds to our target configuration. The second column and third column shows optimized 3D configurations and optical images based on this proposed inverse design method. And the last column corresponds to the initial 2D pattern with the red color denoting the bonding paths. If you look at the right bottom example, you will see we can extract the key ribbon sketches of a frog as our design target. And here the experimental results indeed reproduce well this desired 3D configuration. And this slide, the inverse design of curved 3D surfaces is more challenging. And here we propose a strategy to solve this problem approximately by discretizing desired 3D shapes into 2D ribbon components and using the spatial cyclic distribution to achieve the target curvature distribution. And this method works very well for the centrally symmetric surfaces. And here are three examples. And these two videos illustrate the process of 3D assembly for this hemisphere and this dome-like structure. And this slide provides a few more examples of 3D surfaces, including three general surfaces without any central symmetry. Here we introduce concepts induced by the CT to discretize the surface into a set of curvy ribbons. And then we can leverage the analytical solutions of ribbon-based inverse design to reconstruct this target 3D surface. And good agreements can be observed between our target and the optical images of our structural samples. And this illustrates the general applicability of this inverse design method. Then in terms of the diverse driving forces of the 3D assembly, we have explored a few different options in addition to the pure mechanical forces. And here I want to choose the electromechanically controlled assembly as an example for illustration. In particular, we propose to use dielectric elastomers to serve as a substrate. And we know that the dielectric elastomers sandwiched between two covalent electrodes can be used as an actuator. This is because of the attraction of the opposite charges. And such an electrical actuation can be utilized to drive the 3D assembly, as you can see here. So the expansion of the electrode area can trigger the deformation of the 2D thin film into the desired 3D configuration. On the left of this slide shows two examples of the electrically controlled assembly, including a frog-like structure and a bistable mesostructure. So here, if you look at this video, okay, you will see the formation of a pop-down mode if you do this loading pass 1, okay? This is the loading pass 1. But if you do the loading pass 2, then you will get a different 3D shape with a pop-down, pop-up mode. And this pop-down and pop-up mode can be reshaped quickly between each other. And this electrical loading can be combined with the mechanical loading to achieve a rapid reversible reconfiguration for the 3D structure. So in short, you can mechanically assemble this dome structure first, and then you can apply voltage to achieve the reconfiguration process. So here are two videos, okay? And this reconfiguration can be completed very fast, in just 1 second. So it's a very fast reconfiguration process. Next, I would like to show you some applications of this mechanically guided 3D assembly. And the first one is a 3D electrically small antenna that can offer large frequency bandwidths and small physical sizes. Among the diverse 3D geometries, hemispherical shapes are very promising because they are proved theoretically as an ideal shape for the electrically small antenna. And here, with the use of the developed inverse design method, we can build a flexible and stretchable electrically small antenna with a shape you can see here very close to a hemispherical shape. So if you look at the data of the quality factor over its fundamental low bound, you can see that this hemispherical shape antenna show very outstanding performance. And additionally, the 3D antenna is stretchable and compressible, and therefore it can adapt to changes in the environmental conditions. The second application relates to a spy antenna. And this figure shows the exploded view of the device design. At the center of the device, we designed 3 antennas to cover a wide range of operation frequency from 5 GHz to 30 GHz. And according to 3D assembly with simultaneous release, this 2D device can be transformed into this shape 1 mode. And this is the working mode because the antennas are elevated and exposed to communicate with the external singulars. But when you do sequential release, this structure will be reshaped into this shape 2 mode. And this is the concealing mode. Here, the metal support covers the antennas, and therefore the antennas are electromagnetically shielded. And in other words, this device cannot be detected by the external equivalent in this shape, so we call it a spy antenna. The next one is a reconfigurable antenna with tunable radiation pattern. And this is realized with the loading path controlled method and the bottom-up design strategy. So here, the left top image shows the 2D precursor of a bistable wave antenna. And this, its phase diagram is shown here. So here, the rise mode corresponding to this green color, and this lay mode corresponds to this yellow color. And this rise mode occupies around 45 degrees of the entire loading conditions. And by using this wave antenna as a fundamental element, we can integrate 10 pairs of these elements to form a highly reconfigurable antenna. And this antenna has around 20 different stable configurations based on this reconfiguration strategy. And the bottom images provide 2 representative images of this stable configuration. If you look at the radiation pattern of this antenna, you will see each stable configuration has a main direction, as you can see here and here. And based on our reconfiguration strategy, the main direction of this antenna can be adjusted among 20 different angles. So this means that this single antenna is able to achieve a very densely distributed beam scanning. And such a flexible antenna can be deformed easily to adapt to the complex curvilinear surfaces or time-varying surfaces. And these are very challenging to achieve previously. And in addition to the radiation pattern, the working frequency can be also adjusted in a very wide range based on the reconfiguration design as we show here. So here we use a 3D assembly process to design a class of mechanically triggered switches. And then we integrate them in series to form a dipole-like reconfigurable antenna. And this mechanically triggered switch is composed of 2 different ribbons with different heights. And the antenna, this switch is turned on when the 2 ribbons contact each other. So this this on-off state can be actively controlled by pulling the substrate. And the entire antenna, each arm of the antenna consists of 4 mechanically controlled switches, which separate the antenna into 5 segments. Therefore, it enables 5 different working spaces corresponding to different operation frequencies, as you can see here. So these results indicate that this resonant frequency can be tuned from 2.3 gigahertz to 7.7 gigahertz, representing a very broad range tunability. In the flexible antennas, we have also developed some interesting devices of 3D flexible MEMS, and they can enable accurate measurements of the fluid properties as well as the low frequency energy harvesting of vibration. Due to the time limit, I will skip this part, and you can read these papers if you are interested. Then I would like to make a short summary of the mechanics-guided 3D assembly. This work actually represents a blending of origami and kirigami arts with the mechanics theories, and the result is a 3D assembly approach for high-performance materials. As compared to the other mainstream approaches, the key advantage of this approach lies in the applicability of different material types, feature sizes, and operation speed. The research I introduced today were done in collaboration with many superb research groups. In particular, I would like to thank Professor Yinggang Huang and Professor John Rogers from Northwestern University. We collaborated in the mechanics-guided 3D assembly. Professor Daiyun Fang from Beijing Institute of Technology. We collaborated in soft mechanical metamaterials. Professor Zheng Yan from University of Missouri, and Professor Weng Huang from Hefei University of Technology. We collaborated in the 3D flexible electronics. Also, I would like to thank all the members of my research group. It is them who did all of those works I introduced today. Additionally, I would deliver my thanks for the funding support from the National Nature Science Foundation of China, Ministry of Education of China, Tsinghua University, and Henry Falk Education Foundation. With that, I would like to close and thank you for your attention. Thank you.
Thanks for Yihui, Professor Yihui Zhang's very wonderful talk. And we already received several questions for you. And are you prepared for it?
Sure.
Okay, I will go through. The first one is thanks for the wonderful speech. Yeah, it's very great talk and so many dedicated architecture materials and structures. The question is I would like to ask whether 3D printed materials have biological properties in the field of artificial organs, such as biocompatibility, biodegradability, or self-growth characteristics. That's a very interesting question.
Okay, this is a very good question. Actually, the soft network material designs we have introduced today can apply to a range of different materials, including the biocompatible materials polymers, metals, and many other different materials. Actually, no matter what kind of materials you use, the soft network designs can offer the kind of biomimetic J-shaped stress-strain curves and many other different mechanical properties. So actually, you can utilize the recently developed 3D printing techniques of biocompatible materials to fabricate those soft network materials. And in that case, the resulting 3D network materials will offer the required biological properties you need. And the commercial 3D printer usually do not offer this kind of bio-related properties. Okay.
Okay, great. I think there already have some bio 3D printers which can print the bio tissues and also the hydrogel materials. Maybe they can apply the combined with your research. Okay, let's go to the second question. Yes, you use the water swallowing or thermal expansion method to deform the 2D metamaterial. How is the deforming speed? Have you thought to use the magnetic or electrical method to accurate the deformation?
Yeah, this is a very good question. Very good points. Actually, I'm sorry. If we use water swirling, and then it's quite slow, and the entire deformation process can take around 1 hour or several hours to complete, depending on the specific designs you use. But for the thermal expansion, if you use the electrically controlled heating, then the process can be quite fast, which takes just several seconds to complete. And for the second point of your question, yes, indeed, we have tried to use some magnetically controlled method to deform these responsive materials, and our ongoing projects still take several additional months to finish. And it's very interesting. By using the magnetical control, we can control the structure wirelessly. So that's a good advantage by using the magnetic control. And for the electrically controlled method, we have actually used this kind of control in the thermally controlled metamaterials. And in today's talk, I did not have enough time to expand on that topic. Yeah, that's all for this.
Yeah. Okay, I think Yihui can have some drink and to clear his voice. And then I go to the next question. And Professor Zhang, beautiful work. For the highly stretchable structures combined by different pattern in your slide, can it also be different materials? How to solve the problem of interface? Another interface questions.
Mm-hmm.
Take your time, Yihui.
Sure. I am understanding that this question is relating to the second part of my talk. So this is also a very good point. Actually, for the mechanics-guided 3D assembly, this approach works very well for many different types of materials, including the inorganic semiconductors, metals, polymers, and even ceramics and integrated circuits. So the material is not a problem. And also you can do combinations of multiple materials in a single structure. Regarding the interface, there will be indeed interface between the hard material and the elastomer substrate. So to ensure a good interface, a strong interface between the hard material and the soft material, we have developed some surface chemistry techniques which can create covalent bonding between the different materials. And we have also characterized the interface between the hard and soft materials, and they are regarded to be very strong, comparable to the interface energy of covalent bonding. So I think this is also not a hard problem, and it can be solved.
Okay, let's go to the fourth question. Hello, Professor Zhang, let's talk. I want to know what are the applications of the structure with different regionalized Young's modulus?
Okay, this is also a very good question. And I think this question is related to the responsive mechanical metamaterials in our study. So in that part, we can change the configuration of the microstructures in the metamaterial so as to change the mechanical properties of the metamaterial. And by using the materials with different mechanical properties, it can have important implications in the soft robotics. So in soft robotics, there are many scenarios. They need the robotics to be hard or soft to confront different application scenarios. And I think this is a good application scenario for this kind of material. Thank you for this question.
Okay, a follow-up with this question, I think Yihui, you talk about the soft robotics. It definitely is a very good application field. But my question is that you have to rely on your substrate, right? Stretching your point cannot leave your substrate, right?
Actually, we can separate our 3D structure with the substrate, but due to the time limit, I do not have time to introduce the techniques we developed in this area. Actually, we can use either metal plasticity to memorize this 3D shape. We can also use the chip memory polymers in our technique to memorize the permanent 3D shapes. So we can achieve this.
Great. Okay, let's go to the next question. Thanks, Professor, for the nice talk. I wonder what are the specific application of the buckling structure. I think Yihui already in his last part already talked several applications fields such as different architecture of the antennas, right? Maybe you can answer this question.
Sure.
Yeah.
Sure. This is a very important part of this work, and actually we have spent lots of time on these applications because of our 3D assembly approach represent a unique type of manufacture approaches for the 3D flexible electronics. So we can achieve many different 3D devices that are unachievable previously. So this can open up many new application opportunities. And in our group, we are interested in the unusual electromagnetic devices such as antennas with different reconfigurable working frequencies or radiation patterns. We can also achieve the kind of spy antenna, and also there are many other electromagnetic devices that you can achieve. And in addition, you can also use this technology to achieve some unusual 3D maps. For example, you can use the 3D maps to achieve low frequency wideband energy harvesting. Even when the device is very small, you can still harvest the low frequency energy. And also, there are many application opportunities in the biomedical devices because our 3D structure can provide a very good interface with the soft biological tissues and even cells. So this can provide a good platform to interact with biological tissues. You can do some electrical stimulation and monitoring the electrical and mechanical signals from the tissues. So there are indeed many opportunities. So all of you are welcome to use this technique. Thank you for this question.
Great. See, many audience are very interested in your talk. So we have the bonus question. Usually we have 5 questions, and here we have one more for you. It's a relatively long question. I go through it. And about the biomimetic structure, the string characteristic of the structure is anisotropic. However, which of the real skin is isotropic? So to some extent, as to the string characteristics, the structure is mostly different from certain position body skin, like back or abdomen. Is that contradicted to the meaning of the biomimetic?
This is a very interesting question. So actually, the skin have different compositions, especially for people with different ages. There can be even some wrinkles on the skin, and if the wrinkles appear in the skin, it's definitely anisotropic. But for some other locations and for young people, the skin is more possible to be isotropic. And actually, in our study, we used the mechanical testing results of real skin, which were done by other groups previously. And we just use that results to show the capability of our soft network design to reproduce accurately these mechanical responses. And if the real skin have some anisotropic mechanical responses, we can also adapt this, modify this soft network to yield desired anisotropic mechanical responses. So I think this is not a problem. And for both isotropic and anisotropic mechanical responses of the biological tissues, we can always use this soft network material to reproduce their mechanical property. So I think it's okay to use the biomimetic property, the word biomimetic for that.
Great. Thanks for the wonderful talk and also the good answers to these questions. And the time is perfect also. Thanks, Professor Yihui Zhang from Tsinghua University again. And I think this is also the certificate for the Professor Yihui Zhang. Congratulations and thank you. And then I go back to our beautiful and intelligent Alice and go to our chair. Yes, please.
Okay, thank you very much, Tim, and thank you very much, Yihui. Really wonderful talk. Enjoy a lot. Professor Tim, please prepare your slides. You are invited to join us. Yeah, so I think Yihui give you some pressures. Right? Yeah, Yihui's talk was really wonderful, rich of the content. So, Tim, I give you 1 or 2 months. You prepare your talk, okay? Yeah. So, Yihui, yeah, I have a chance to meet you in person. I think I will deliver the hard copy to you very soon. Yeah. So, thank you, and your flexible, 3D structures are really, really interesting. We're looking forward to have more and more, interesting questions come out. So next week, yeah, we're going to have Paula from MIT and Andrew from UCLA. So both of them are very famous, well-known scientists on the world. Paula was amazing person, amazing lady. He was, elected to National Academy of Engineer and Science and Biomedical and Innovation, many. So yeah, she is the most, influence the female scientists in the whole world. So next week she's going to give us stories for using the biomaterials to make different structures and different devices. Andrew Neil was MD. So he's going to talk about a very hot topic, how we can get the COVID-19, to get over. So he developed some kind of very nice, works here. So yeah, we're going to have, Andrew and Paula on the ICANX stage next week. I really looking forward to their talks. And next week we have Paul as our super, guest here. He's going to chair the sessions. So that's next week. But before next week, I will going to deliver a talk in Chinese. On this I Can Ask talk is for the innovation. Today our speakers, our VIP guests already mentioned that for all the students, the most, important part, the skill is innovation, is creativity. So, this Sunday, I will going to deliver talk, Sunday morning, 9:30, I'm going to deliver talk, I Can Ask. It's about innovation and entrepreneurship and how you do it, how to get it started. So there are a lot of stories, a lot of interesting encouragement, and some methods and some kind of skills, tools to deliver to you. So stay with I Can Ask. There are a lot of things, to go with you and to, have more and more kind of interesting, lectures, actions to you. So yeah, please stay with I Can Ask. We're going to have more and more speakers here. We're going to have more and more new technology here. So new science here. So that's I Can Ask. I think, that's the world largest, the science talk. And every Friday, I see you at 8 o'clock. Okay, that's enough today. Let's see, what we're going to have next week. So we'll have more and more, to enjoy. Bye bye. See you next week.
Bye bye. Thank
Bye-bye.
you. Thank you.
Thank
Bye
you.
bye. Bye. Yihui工作很棒啊，做的真的非常好。
Hello， 嗨，哇，一会讲得很棒，
真的很棒，真的很棒。
对，
获奖，再次感谢。
一会太认真了，
对，
这个搞得
非常好
张挺同志。